Hey guys, and welcome back to Optimal Programming. In this video, we will talk about the history of computers and how it developed over time. So let's get to it. Before the age of electronics, the closest thing to a computer was the abacus. The universal language in which computers carry out processor instructions originated in the 17th century in the form of the binary number system. Developed by German philosopher and mathematician Gottfried Wilhelm Leibniz, the system came about as a way to represent decimal numbers using only two digits, the number 0 and the number 1. Leibniz's system was partly inspired by the explanations in the classical Chinese texts, which explained the universe in terms of dualities, such as light and dark and yin and yang. While there was no practical use for his newly codified system at the time, Leibniz believed that it was possible for a machine to someday make use of these long strings of binary numbers. In 1847, English mathematician George Boole introduced a newly devised algebraic language built on Leibniz's work. His Boolean algebra was a system of logic with mathematical equations used to represent statements in logic. It employed a binary approach in which the relationship between different mathematical quantities would be a duality, true or false, or 0 or 1. Just like Leibniz, there were no applications for Boole's system at the time. However, mathematician Charles Sanders Peirce spent decades expanding the system and in 1886 determined that the calculations could be carried out with electrical switching circuits. As a result, Boolean logic would eventually become instrumental in the design of electronic computers. English mathematician Charles Babbage is credited with having assembled the first mathematical computers, at least technically speaking. His early 19th century machines featured a way to input numbers, memory, and a processor, along with a way to output the results. Babbage called this initial attempt to build the world's first computing machine the difference engine. The design called for a machine that calculated values and printed the results automatically onto a table. It was to be hand-cranked and would have weighed 4 tons. But Babbage's machine was a costly endeavor. More than 17,000 pounds sterling was spent on the difference engine's early development. The project was eventually scrapped after the British government cut off Babbage's funding in 1842. This forced Babbage to move on to another idea, an analytical engine, which was more ambitious in scope than its predecessor, and was to be used for general-purpose computing rather than just arithmetic. While he was never able to follow through and build a working device, Babbage's design featured essentially the same logical structure as electronic computers that would come into use in the 20th century. The analytical engine had an integrated memory, a form of information storage found in all computers that allows for branching, or the ability for a computer to execute a set of instructions that deviate from the default sequence order, as well as loops, which are sequences of instructions carried out repeatedly in succession. Despite his failures to produce a fully functional computing machine, Babbage remained steadfastly undeterred in pursuing his ideas. Between 1847 and 1849, he drew up designs for a new and improved second version of his difference engine. This time, it calculated decimal numbers up to 30 digits long, performed calculations more quickly, and was simplified to require fewer parts. Still, the British government did not feel it was worth their investment. In the end, the most progress Babbage has ever made on a prototype was completing 1/7 of his design. During this early era of computing, there were a few notable achievements. The tide predicting machine, invented by Scotch-Irish mathematician, physicist, and engineer Sir William Thomson in 1872, was considered the first modern analog computer. 4 years later, his older brother James Thomson came up with the concept for a computer that solved mathematical problems known as differential equations. He called his device an integrating machine, and in later years it would serve as the foundation for systems known as differential analyzers. In 1927, American scientist Vannevar Bush started development on the first machine to be named as such, and published a description of his new invention in a scientific journal in 1931. Up until the early 20th century, the evolution of computing was little more than scientists dabbling in the design of machines capable of efficiently performing various kinds of calculations for various purposes. It wasn't until 1936 that a unified theory on what constitutes a general-purpose computer and how it should function was finally put forth. That year, English mathematician Alan Turing published a paper which outlined how a theoretical device called the Turing machine could be used to carry out any conceivable mathematical computation by executing instructions. In theory, the machine would have limitless memory, read data, write results, and store a program of instructions. While Turing's computer was an abstract concept, it was a German engineer named Konrad Zuse who would go on to build the world's first programmable computer. His first attempt at developing an electronic computer, the Z1, was a binary-driven calculator that read instructions from the punched 35mm film. The technology was unreliable, so he followed it up with the Z2, a similar device that used electromechanical relay circuits. While an improvement, it was in assembling his third model that everything came together for Zuse. Unveiled in 1941, the Z3 was faster, more reliable, and better able to perform complicated calculations. The biggest difference in this third incarnation was that the instructions were stored on an external tape, thus allowing it to function as a fully operational program-controlled system. What's perhaps most remarkable is that Zuse did much of his work in isolation. He had been totally unaware that the Z3 was Turing complete, or in other words, capable of solving any computable mathematical problem, at least in theory. Nor did he have any knowledge of similar projects underway around the world in the same time. Among the most notable of these was the IBM-funded Harvard Mark I, which debuted in 1944. Even more promising, though, was the development of electronic systems, such as Great Britain's 1943 computing prototype, Colossus, and the ENIAC, the first fully operational electronic general-purpose computer that was put into service at the University of Pennsylvania in 1946. Out of the ENIAC project came the next big leap in computing technology. John von Neumann, a Hungarian mathematician who consulted on ENIAC project, would lay the groundwork for a stored program computer. Up to this point, computers operated on fixed programs and altering their function. For example, from performing calculations to word processing. This required the time-consuming process of having to manually rewire and restructure them. It took several days to reprogram the ENIAC. Turing had proposed that ideally having a program stored in the memory would allow the computer to modify itself at a much faster pace. Von Neumann was intrigued by the concept and in 1945 drafted a report that provided in detail a feasible architecture for the stored program computing. His published paper would be widely circulated among competing teams of researchers working on various computer designs. In 1948, a group in England introduced the Manchester Small-Scale Experimental Machine, the first computer to run a stored program based on the von Neumann architecture. Nicknamed Baby, the Manchester machine was an experimental computer that served as the predecessor to the Manchester Mark I. The EDVAC, the computer design which von Neumann's report was originally intended, wasn't completed until 1949. The first modern computers were nothing like the commercial used by computers today. They were elaborate, hulking contraptions, and they often took up the space of an entire room. They also sucked enormous amounts of energy and were notoriously buggy. And since these early computers ran on bulky vacuum tubes, scientists hoping to improve processing speeds would either have to find bigger rooms or come up with an alternative. Fortunately, that much-needed breakthrough was already in the works. In 1947, a group of scientists at Bell Telephone Laboratories developed a new technology called point contact transistors. Like vacuum tubes, transistors apply electrical current and can be used as switches. More importantly, they were much smaller, about the size of an aspirin capsule, more reliable, and they used much less power overall. The co-inventors, John Bardeen, Walter Brattain, and William Shockley, would eventually be awarded the Nobel Prize in Physics in 1956. While Bardeen and Brattain continued doing research work, Shockley moved to further develop and commercialize the transistor technology. One of the first hires at his newly founded company was an electrical engineer named Robert Noyce, who eventually split off and formed his own firm, Fairchild Semiconductor, a division of Fairchild Camera and Instrument. At the time, Noyce was looking into ways to seamlessly combine the transistor and other components into one integrated circuit to eliminate the process in which they had to be pieced together by hand. Thinking along similar lines, Jack Kilby, an engineer at Texas Instruments, ended up filing a patent first. It was Neus's design, however, that would be widely adopted. Where integrated circuits had the most significant impact was in paving the way for the new era of personal computing. Over time, it opened up on the possibility of running processes powered by millions of circuits, all on a microchip the size of a postage stamp. In essence, it's what has enabled the ubiquitous handheld gadgets we use every day that are ironically much more powerful than the earliest computers that took up entire rooms. So guys, this is how computers were created and evolved over time. Thank you for watching. Make sure you stay tuned for the next episode and subscribe and press that bell notification so you don't miss a single episode. And I'll see you in the next one.